Good morning, judges. I am Chung Man. We represent Chung International School, and we will present our algorithm to asymptotically efficiently approximate the mean cross-sectional area of 3D convex hulls. Firstly, here are general definitions. We define an orthographic projection as an affine transformation that flattens 3D space onto a plane along the plane's normal vector. The cross-sectional convex hull area of a specific polygon in a specific direction, which we abbreviate as its CSA, is the orthographic projections area of the polyhedron in that direction. And we call the arithmetic mean of a polyhedron CSA across all directions of projection its mean CSA. Our algorithm is deterministic and approximates the mean CSA of any polyhedron with a time complexity of O of a, b, n log n. And there are two positive integer parameters, a and b, which allow for adapting the algorithm to different requirements of accuracy and computational cost. The relative error of our algorithm is bounded, and with a and b set to 9 and 6, the upper bound for relative error is 0.02. This algorithm is much faster for large sets of vertices than brute force calculation, which needs O of n cubed time complexity. Here are some applications for our algorithm, where approximations for the mean CSA or convex hull surface areas of 3D objects are useful. The concept behind our algorithm is that the mean CSA can be approximated by calculating the CSA of a 3D shape from different angles, then finding the mean of all calculated values. Step 1 is to orthographically project the polyhedron onto a plane. Step 2 is to calculate the CSA for a specific direction using the projection. And step 3 is to repeat steps 1 and 2 and then take the mean. We start with step 3, which is to use a Riemann sum to decide which directions to calculate the CSA in, and also to calculate the mean. We use A for the input polyhedron, S for the unit sphere, and D as the direction in which we calculate the CSA. We first define an area preserving map from rectangle U times V onto the unit sphere, so that we can choose equally distributed points on the unit sphere using U and V. And since the mean CSA of any polyhedron is equal to the CSA of any hemisphere, we only care about the pairs of U and V, which map onto the unit hemisphere with non-negative z coordinates. And since the mean CSA can be calculated in terms of CSA in different directions using the mean of continuous function formula. Since the domain is bounded, we can use a double Riemann sum to divide the integral into equal area subdivisions based on U and V. The direction of CSA for each subdivision, d star, is the mean direction of projection in that subdivision. In terms of each subdivision's d star, we can represent the CSA as the limit of this double Riemann sum. So, this equation is our approximation for the mean of the CSA, where m and n are integer parameters of the function. Then step 1 and 2 are to calculate the CSA for each specific direction. Next, step 1 is to orthographically project the input polyhedron onto a plane P. We divide the orthographic projection operation into 3 steps, r, lambda, and sigma. We define B as the result of projecting the input polyhedron onto P. R is a rotation of the projection direction and input polyhedron so that the projection is along the z-axis, and lambda is the projection matrix, and sigma converts the projected points from 3D to 2D coordinates. R can be derived from our equation for D. Here is the derivation for R. The most trivial plane with normal vector along the z-axis is the xy plane, so we use the xy plane as P. The orthographic projection lambda onto the xy plane is equal to this 3x3 matrix. Here is the proof for lambda. And all the points on the xy plane can be represented using 2D coordinates by ignoring the z coordinate in 3D space. This operation is sigma, which is this 2x3 matrix. The entire orthographic projection is the three matrices applied one after each other, equivalent to their products. So the result of the projection of the input polyhedron as a set is this equation for B. Next, step 2 is to find the area of the bounding polygon of the projection, which is the CSA. We define B0 as the bottom left point of the projected set, alpha of any points as the angle from B0 to that point, Bn as the nth point in the projected set from B0 in anticlockwise order, capital N as the number of extreme points excluding B0, C as the convex hull of the projected set, which is an ordered set, and Ci as the ith point in C. The vertices of the bounding polygon are the extreme points of the projected set, so we filter for them using an anticlockwise Graham scan. To order the points in anticlockwise order, we first need each point's value of alpha. Here is the equation for cosine alpha using dot products. Ordering by decreasing cosine alpha is equivalent to anticlockwise ordering of points in the projected set. This takes O of n log n operations because of sorting. We iterate over the ordered points with Graham scan, removing every point that makes a non-left turn with any two other points, because those points cannot be extreme. And here is the inequality for whether a point makes a left turn. The result of the Graham scan is that the extreme points in anticlockwise order. So we calculate for the bounding polygon's area by iterating over each extreme point with the shoelace formula. The result is the CSA for a specific projection. Combining all three steps into one algorithm gives us this Python code. We use two for loops to iterate through each repetition of step 1 and 2, which is... And then we start by calculating the trigonometric functions for theta and psi. And then we apply the 2x3 matrix on each point of the input polyhedron onto the projected set, which is step 1. And then we find V0, and then we use a dictionary to store all the points in the projected set with keys as their value for alpha. This is the dictionary. And then we create an array to store all the points in the dictionary in descending order of keys, and run an anticlockwise Graham scan on that array. The shoelace formula then iterates over the Graham scan's output, and the result is added to our running total. And at the end, the total is divided by the number of total repetitions done to output the mean CSA. Our algorithm has a bounded maximum relative error. Here are 4 pairs for A and B, which guarantee that the relative error is under certain thresholds, or equivalently, above certain relative accuracies. And the relative error is the highest for extremely long or flat shapes, but the error quickly converges, unless the shape is relatively thin along the z direction, where relative error instead approaches 0. Thank you.